Welcome to your deep dive. We're going to unlock some secrets about the cosmos, and it's all thanks to the research that you wanted to explore.
Oh, very nice.
This brand new paper, Vertical Kinematics of Young Galactic Clusters.
Okay.
And it was just published this month, January 2025, so we're right on the cutting edge here.
Yeah, it's always so exciting to jump into the latest findings, especially when they kind of challenge our understanding of the galaxy as a whole.
Yeah, and this one really
Yeah.
does, it tackles this fascinating mystery. Why do young star clusters, those baby stars hanging out in groups, seem to move so differently than older stars in the Milky Way? It's like they're dancing to a different tune.
Yeah.
And the best part is these movements can reveal clues about the hidden structure of our galaxy.
Absolutely. These seemingly simple movements can offer a really unique window into how the Milky Way works.
So to decode this cosmic dance, the researchers use something called a vertical phase diagram. Now, I know that sounds like something straight out of Star Trek, but it's actually a pretty cool way to visualize how stars are moving up and down relative to the galactic disk.
Right.
Think of it like tracking the ups and downs of a roller coaster, but on a galactic scale.
Yeah, it's a powerful tool for understanding stellar kinematics.
Oh, for sure, for sure.
Allows us to see patterns that might otherwise be hidden, in the vastness of space.
So let's zoom in on these youngsters.
Okay.
The researchers focused on two catalogs of young open star clusters, the DYOC and the GYOC.
Got it.
These catalogs include clusters that are practically newborns in cosmic terms, less than 50 million years old.
Wow.
To put that into perspective, our galaxy is billions of years old,
Mm-hmm.
and they're all relatively close to us within about 3.5 kiloparsecs.
Okay.
Now, a kiloparsec is a unit of distance astronomers use.
Right.
1 kiloparsec is about 3,260 light years.
Right. We're essentially looking at stars in our cosmic backyard,
Yeah.
which makes this study even more relevant to our understanding of our place in the Milky Way.
Okay, so we've got these baby star clusters in our sights. The researchers used a sophisticated method to map out their movements, kind of like creating a 3D model, a Google Maps for baby stars, showing not just where they are, but also where they're headed. What they found was really surprising. The youngest clusters, those under 30 million years old, show a very distinct pattern in their movements. They're moving up and down in a way that's directly proportional to their distance from the galactic disk.
It's like they're following a set of rules,
Totally.
a cosmic choreography that is remarkably consistent for these young clusters.
But here's where things get really interesting. Older stars don't follow this pattern at all.
Right.
Their movements are much more complex. We know this thanks to data from the Gaia Space Telescope,
Yeah.
which has been mapping the movements of billions of stars. It's like the older stars decided to ditch the choreography and just freestyle it.
So the question is, why do these young clusters follow this predictable pattern? What force is guiding their dance? And the researchers propose that it's the gravitational pull of all the matter in the galactic disk, stars, gas, dust, all of it working together like a giant cosmic spring.
A cosmic spring. Okay, I'm intrigued. Tell me more about this.
Okay, so imagine a weight bobbing up and down on a spring.
Okay.
The weight moves away from its resting position, the spring pulls it back, it overshoots, gets pulled back again, and so on. The researchers suggest that the young star clusters are behaving in a similar way. They move away from the galactic disk. The gravity of all the matter in the disk pulls them back, they overshoot, and the cycle continues.
So it's like the whole galaxy is acting like a giant trampoline, and these young clusters are bouncing up and down on it.
Yeah, that's a great analogy. And here's where it gets really cool. The slope of that line we see in the vertical phase diagram, the one that shows the relationship between the cluster's distance from the disk and its velocity, that slope is directly related to the density of matter in the sun's neighborhood. The steeper the slope, the denser the matter.
So by studying the movements of these young clusters, we can actually measure how much stuff is packed into our little corner of the galaxy.
Exactly.
That's amazing.
It's like using these clusters as cosmic scales, weighing the invisible matter around us. And what they found is truly remarkable.
Okay, drum roll, please.
Oh, wow.
What did they find? How much does our cosmic neighborhood weigh?
They estimated the average density of matter in the sun's neighborhood to be between 0.09 and 0.15 solar masses per cubic parsec.
Right.
Now, a solar mass is simply the mass of our sun, and a parsec is another unit of distance astronomers use. 1 parsec is about 3.26 light years.
Okay.
So we're talking about how much mass is packed into a cube of space that's about 3.26 light years on each side.
Okay, help me understand the significance of that number. Is that a lot? A little.
What's fascinating here is that this density estimate is consistent with previous estimates obtained using completely different methods.
Hmm.
It confirms that we're on the right track in our understanding of the matter distribution in the galaxy.
So this isn't just some random number. It's a major validation of this new method for studying the galaxy, right?
Absolutely.
It's telling us that these young star clusters are reliable probes of the galactic environment, and that their movements can reveal valuable information about the distribution of matter. But here's where things take an interesting turn. While this simple model works beautifully for the youngest clusters, once they hit about 40 million years old, things start to change.
Interesting.
Wait, so they hit a cosmic midlife crisis and their movements get less predictable? What's going on there?
That's exactly what we'll explore next.
Okay.
As the clusters age, they encounter more complexities in the galactic environment, and their dance becomes less about following a simple set of rules and more about navigating a cosmic mosh pit.
Okay, I'm hooked. Let's take a deep dive into this cosmic mosh pit.
Okay.
Tell me everything.
So as these star clusters age, they start to deviate from that nice, neat pattern we saw with the younger ones. Right.
Their movements get more complex, less predictable. Imagine those graceful ballet dancers we talked about suddenly finding themselves in a mosh pit.
Okay, that's quite the image. So what's causing this shift? Are these clusters getting influenced by the older, more chaotic stars? Is it some kind of cosmic peer pressure?
Not quite peer pressure, but they are definitely feeling the effects of their environment.
Mm.
The paper suggests a few different factors might be at play.
Okay, lay it on me. What kind of galactic forces are messing up their moves?
Well, for one, there are the spiral arms of our galaxy.
Right.
These vast structures of stars and gas exert their own gravitational pull.
Mm-hmm.
As the clusters move through the galaxy, they might encounter these arms,
Yeah.
getting tugged and nudged in different directions.
Uh-huh.
Think of it like navigating a crowded room. You're bound to get bumped around a bit.
I can definitely relate to that. So it's like those spiral arms are throwing a cosmic party, and these clusters are trying to make their way through the crowd.
Exactly. And then there are transient events like supernovae.
Those explosive deaths of massive stars. These events release tremendous amounts of energy and can really shake things up,
Wow.
disrupting the motions of nearby star clusters.
Whoa, talk about a party foul. So as these clusters age, they're exposed to more of these galactic forces, and their movements get more chaotic. Is there anything else?
Yeah, the researchers also suggest that the overall structure of the galactic potential,
Okay.
the underlying gravitational landscape of the galaxy, might not be as simple and symmetrical as we sometimes assume.
Okay.
This could also lead to more complex stellar motions.
So it's not just about the individual forces they encounter, but also the overall shape of the galactic playground they're moving through.
Precisely. It all adds up to a more complex dance for these older clusters.
So we've got these baby star clusters moving like clockwork, but as they age, they enter this cosmic mosh pit, and their movements get more complex. It makes you wonder if they're so sensitive to their galactic surroundings, can we use their movements to learn even more about the Milky Way?
That's a great question, and that's exactly what the researchers are hoping to do. They see these clusters as a new tool for probing the structure and evolution of our galaxy.
I'm all ears. Tell me, what kind of secrets might these clusters be hiding?
Well, by studying the deviations from that simple up and down motion, we might be able to map out the distribution of those spiral arms and other large-scale structures in the galaxy. It's like using these clusters as tiny cosmic surveyors charting the invisible landscape of the Milky Way.
So they're not just dancers, they're cartographers too. That's pretty cool. What else?
Their movements can also help us understand the distribution of matter in the galaxy.
Okay.
Remember, the more massive a region is, the stronger its gravitational pull.
Right.
By studying how these clusters respond to those gravitational forces, we can learn about where the matter is concentrated.
So by studying their movements, we can actually weigh different parts of the galaxy.
Exactly. It's like using these clusters to create a 3D map of the Milky Way's mass distribution. And who knows, we might even be able to detect the faint gravitational influence of dark matter.
Whoa, dark matter. Okay, now we're talking about some serious cosmic mysteries. But before we get too lost in the dark matter rabbit hole, let's bring it back to these clusters. We've talked about how their movements can reveal clues about the structure and matter distribution of the galaxy. But the paper also hints at something even more intriguing.
You're talking about how these clusters evolve over time, how they lose mass as they age.
Yes. This is where it gets really fascinating. Remember how the researchers divided those clusters into different age groups?
Right, like sorting them into different cosmic playgroups based on how long they've been around?
Exactly. And they found that the slope of that line in the vertical phase diagram, The one that tells us about the density of matter actually changes depending on the age group. It seems strange to me. Are the laws of gravity changing over time?
No, gravity's not changing, but the clusters themselves are. As they age, they start to lose members.
Okay.
Some stars drift away, no longer bound by the cluster's gravity.
It's like those cosmic playgroups are shrinking as some of the kids wander off to explore the galactic playground on their own.
Exactly. And as the clusters lose members, their overall mass decreases. This means their gravitational pull weakens, which affects their movements, and in turn, that slope in the vertical phase diagram.
Ah, I see. So a less massive cluster would have a less steep slope because it's contributing less to the overall density.
Precisely. And this opens up a whole new avenue for studying the evolution of star clusters and the dynamics of the galaxy. By carefully measuring the slopes for different age groups, we might be able to track how clusters lose mass over time.
So it's not just about measuring the density of matter anymore. It's about using these clusters to understand how they themselves change and evolve over time.
Exactly. And by understanding how they evolve, we can gain insights into the forces that are shaping them. We can learn about those spiral arms, those supernovae, all those galactic forces that are tugging and pushing on these clusters, causing them to lose members.
This is incredible. We started with these baby star clusters bobbing up and down like weights on springs, and now we're talking about using them to track the evolution of star clusters and uncover the hidden forces shaping our galaxy. I'm sensing a but coming.
Yeah, you're right. There is a but. It's not all smooth sailing from here. Even with all this amazing potential, there are still challenges to using these star clusters as galactic probes.
That's true. It's a complex puzzle, and there are still pieces missing. For example, while we can track the movements of these clusters and measure their mass loss, it's still difficult to pinpoint the exact causes. Is a particular cluster losing mass because it's passing through a spiral arm, or is it because a nearby supernova shook things up? It's hard to say for sure.
So it's like watching the aftermath of a cosmic billiards game. You can see the balls scattering, but you're not sure who made the first shot. Exactly. Teasing apart the individual contributions of these different galactic forces is still a major challenge. And then there's the issue of dark matter. We know it's out there exerting its gravitational influence, but it doesn't interact with light, so it's incredibly difficult to detect directly.
But you mentioned earlier that we might be able to use these clusters to learn something about dark matter. How would that even work?
Well, if dark matter is concentrated in certain regions of the galaxy, which is what we believe, then it should affect the movements of nearby star clusters. Even though we can't see the dark matter directly, we can see its effects on the things around it.
So it's like watching a puppet show. You can't see the puppeteer, but you can see the puppets dancing.
That's a great analogy. By carefully studying the motions of these clusters, especially the ones that seem to be moving in unexpected ways, we might be able to infer the presence and distribution of dark matter.
This is blowing my mind. We started with these baby star clusters, and now we're talking about using them to map dark matter, one of the biggest mysteries in the universe. What an incredible journey.
It really highlights how much we can learn from these seemingly simple objects. They're not just stars grouped together, they're dynamic systems constantly evolving, interacting with their environment, and revealing secrets about the galaxy we call home.
This deep dive has taken us from the familiar, those twinkling stars in the night sky, to the truly mind-boggling, the structure of the Milky Way, the invisible pull of dark matter, the evolution of star clusters over millions of years. It's amazing how interconnected everything is.
It really is. And this is just the beginning. As we continue to gather more data, develop more sophisticated models, and refine our understanding of the galaxy, who knows what other discoveries await us.
I can't wait to see what the future holds for this field of research. Maybe one day we'll be able to use these star clusters to map out the entire Milky Way in exquisite detail, uncovering its hidden structures and unraveling the mysteries of dark matter.
It's a thrilling prospect, isn't it? And to think it all started with those seemingly simple movements of young star clusters, it's a testament to the power of curiosity, observation, and the relentless pursuit of knowledge. So keep looking up, keep asking questions, and keep exploring the wonders of the universe. You never know what you might discover.